The single most important takeaway I want to share with you today is that sharing your elevation information over time is unsafe. So here's the question. How come knowing your position with respect to the sea level affect your privacy? In this work, we discover the potential risks of sharing elevation information as part of workout data and demonstrate that it indeed risks users' privacy. My name is Ülkü Meteris, a PhD candidate at University of Central Florida, and in this video I will be showing you how to reveal the location of a user from a shared elevation profile from an exercise activity and the associated privacy implications. Here's the brief outline that we are going to follow. First, I will discuss the motivation and the problem. Then, I will introduce the potential threat models under which the experiments are conducted. Later, I will move on with the details of the method. After that, I will share our findings in the evaluation section. Finally, we will briefly touch the previous work and conclude the presentation. Let's dive in with the motivation. From smartphones to wearable devices, various types of IoT devices are equipped with GPS, accelerometers, and gyroscopes to allow applications to function or to present a better user experience by making use of geodata, such as location and elevation information. Specifically, fitness applications which run on smartphones and smartwatches use these systems to collect spatial, temporal, and activity-specific information to analyze, summarize, and visualize users' activity. Despite the broad set of advantages geodata has, geodata usage and uncontrolled sharing can pose a significant privacy risk, which can be exploited in multiple attacks, including stalking and cybercasing. With the large amount of the geotech data, including text, images, and videos, cybercasing allows a significant attack vector to maliciously motivated individuals. Geotagged photos that are frequently posted on image sharing websites or second-hand sale websites may put owners of those images at risk. For example, geotagged images posted on sales website may reveal the location of the advertised product, leading to trespassing or even theft. While geodata recorded by fitness applications is indeed important and valuable for the operation of those applications, it also can be used for launching attacks on users by breaching their privacy. Even worse, a large number of users, when sharing such information, would be unaware of the ramifications of sharing and the potential risk of inferring such contextual information from this shared location data. To support this argument, we conducted an online survey with 60 participants who regularly use fitness applications outdoors. The survey results reveal that 51% of the participants start their training from their homes, 36% start from their school, and 3% start from their workplace. And 76% of the participants finish their training at their homes. Moreover, for the same set of users, 42% of those users have indicated that not sharing location information implies privacy protection. 30% of the respondents were uncertain, and 28% were certain that not sharing would not necessarily mean their privacy is protected. This kind of mixed responses highlight the gap between reality and expectations of privacy when sharing location information online, and call for further investigation. Although it is possible not to share the location trajectory by hiding the activity map in the fitness applications, users still want to share elevation profile or certain statistics of the activity to show the roughness, technicality, and difficulty of the routes they took as a measure of their workout. For example, recently, users have been demanding those fitness applications to allow for fine-grained and customized access control by allowing them to share the elevation profile of an activity while masking the map, which has the highest privacy value. However, is sharing the elevation profile of an activity enough to maintain the privacy of the users? In this study, we argue that an approximate location extracted from context of activities could still be revealed from elevation profile information. We examine this problem at length and develop approaches that can be used to accurately associate an elevation profile with contextual information, such as location. Our key contributions are as follows. We translated the problem into text and image classification problem by encoding the elevation signals as strings and visualizing the elevation signals as images to employ the common approaches for solving image and text classification problems. We investigated the possible attack surface for the problem by introducing 3 different threat models, which we later used to evaluate the success of our approach by simulating our methods considering each of these threat models. We proved that the location information can be predicted from elevation profile using different machine deep learning methods with accuracy in range 59% to 95% at different resolutions. Let's define our threat models. We have 3 threat models. In threat model 1, we assume an adversary with records of the workout history of a target user, and the goal of the adversary is to identify the last workout location of the target user from the shared elevation profiles. TM1 is justified by multiple plausible scenarios in practice. For example, such an adversary might have been a previous social network connection of the target user that was later blocked. In such scenario, the adversary may save previous workout records of the target. Another example might include group activities in which the adversary and the target may have shared the same route at some point. In either case, by knowing the target's history, the main goal of the adversary in this model is to identify recent whereabouts only from publicly shared elevation profiles, thus breaching the target's privacy. In threat model 2, we assume an adversary with access to limited information such as the city in which the target lives. Such information is easily accessible from public profile summaries at links.com, public records, etc. The adversary's goal in TM2 is to find out which region or part of a given city the target activities are associated with. The adversary, knowing the city where the target lives, would want to identify the region associated with the user's activity. In threat model 3, we assume an adversary trying to identify the target user's city using only publicly shared elevation profiles. The use scenario of TM3 may be used as a stepping stone towards launching the attack scenario in TM2 upon narrowing down the search space to a city. The adversarial capabilities in TM1 are greater than in TM2 and TM3, making it more restrictive, powerful model. Now that we have defined the problem, let's see how we can tackle it. Our pipeline consists of the data collection, pre-processing, feature extraction, and classification respectively. Let's start with the data collection. In this study, we compiled 3 datasets: the user-specific dataset, the city-level dataset, and the borough-level dataset. For the user-specific dataset, we collected activity samples including each activity's location trajectory and the corresponding elevation profile from a voluntary athlete who records activities frequently. To label the samples, we fetch the maximum and minimum coordinates of each location trajectory. Each sample location trajectory is encapsulated with a tight rectangle whose top right and bottom left corners are computed from a maximum and minimum coordinates of the trajectory as illustrated. To classify the samples, each rectangle encapsulating the trajectory is compared with the previously created regions. If the Euclidean distance between the center of the rectangle and the center of the existing region does not exceed a predetermined threshold, the rectangle and its corresponding sample are labeled with a unique identity of the region. If there is no region that includes the trajectory, a new region is created. For the city-level and borough-level dataset, we mined publicly available training route segments in a popular fitness tracking application using its Explore segment functionality. Segments are user-created activity routes whose main purpose is to compare completion times among users. These routes are particularly useful since they include location trajectories which are frequented by actual users rather than randomly created location trajectories. The overall mining process consists of 3 steps. First, we define the cities of interest, which are also the class labels. For each city, we define rectangle boundaries B consisting of corner coordinates. Explore segments returns only top 10 segments encapsulated by a given boundary. Therefore, to obtain more data of a city, we divided the large rectangle boundary of the city into smaller regions, each noted by R and their region boundaries B. For each region boundary B, we called explore segments and received the geolocation polyline paths of the top 10 segments. Finally, we obtained the corresponding elevation profiles for each path using the Google Maps Elevation API. I should note that, unlike user-specific dataset, city and borough level dataset do not include overlapped samples since each region is disjoint with the other regions. In the preprocessing phase, we have text and image-like representations of the samples to facilitate feature extraction. For text-like representation, we employ a four-stage pipeline: discretization, word size decision, text encoding, and vocabulary creation. In the discretization step, the origin elevation signals is discretized along y-axis. This eliminates possible overhead by small differences in the precision, causing a longer string correspondences and consequently longer vocabulary and sparse feature vectors. For word size decision, we use this formulation, where W is the word size, L is the length of the alphabet, and C is the number of unique value occurrences in the given signal. For text encoding, each unique value in all discrete signals is mapped to a unique string with length W. Then, each sample is encoded by referring the string mapping of each value in the discrete signal. Concatenating of these strings constructs our corpus. And finally, we build a vocabulary from unique word-based engrams of the corpus. In image-like transformation, the elevation signals are drawn as line graphs. To draw a line graph, the maximum and minimum values for y-axis are set to the extremes of each elevation signal, and the lines are colored to encode the value interval in which the elevation signal ranges. In text-like feature extraction, words and non-overlapping occurrences of word sequences are counted. A feature vector for each sample is created with each count being a feature. Finally, the feature vectors are normalized. Therefore, each feature represents the probability of occurrence of each word in the given sample. However, when the dataset is large and diverse, the vocabulary and consequently the feature vectors becomes too large and sparse. In feature selection phase, in case the length of the feature vectors are too long, some rarely occurred features from vocabulary are discarded according to the specified feature frequency threshold. For images, we use convolutional neural network. Since the convolutional layer kernels extract features by learning the filters optimally and efficiently, it is unnecessary to explicitly extract features. For classification, support vector machine SVM, random forest classifier RFC, multilayer perceptron MLP, and convolutional neural network CNN are used. We use a standard SVM where the objective is to find the best hyperplane separating classes from one another. We utilize a standard RFC with 100 trees, and majority voting is taken over the outcomes of those trees. We use a standard MLP with 100 hidden layers and Adam solver for weight optimizations. This figure illustrates the employed CNN architecture. Two consecutive convolution layers are used along with the relay activation function and max pooling layers before a fully connected layer. The distinctive features are selected at the max pooling layers with kernel and stride size of 2, which reduces the dimensions from 32 to 8 at 2 passes. The loss is calculated by a cross-on triple loss function, and for optimization, the Adam optimizer is used. Let's discuss the evaluation results. We performed evaluations for each dataset and threat models. First, we performed evaluations with text-like representation. For TM1, we performed experiments using 5 and 10-fold cross-validation and by fixing the dimensions of n-grams to 8 on the user-specific dataset. SVM, MLP, and RFC techniques are used for the classification. The user-specific dataset has unbalanced sample size across classes. To mitigate bias, we use the same sample size for each class and change number of classes at each step. Due to the limited number of samples, the accuracy of 4-class classification is lower than 3 and 2-class classifications. We observe a higher accuracy with 10-fold than when in 5-fold due to the large training data capturing the population's distribution in 10-fold. Since the user-specific dataset is compiled from actual users, about 35% of the routes are overlapped. In a repetitive and overlapped setting, both training and testing splits may contain similar patterns, leading to high accuracy scores. The results prove that a targeted attack on a person whose activity history is known will be successful with accuracy between 86% to 98%. While evaluating TM2, the borough level dataset is used. A separate model is created for each city, and each city is evaluated separately. For all cities, the accuracy is above 55%, while the recall varies. The main reason of the difference in the TM1 and TM2 results is the fact that there is no overlapped or repetitive routes in the borough level dataset. In order to be able to correctly compare the TM1 results with others, we simulated the overlapped datasets and performed the same evaluations. For the TM2 evaluations, we reviewed the simulation dataset with 30 to 34% overlap ratio for each region within the cities. The same evaluation procedures are then followed as the original mined dataset. The bar charts show comparison between the results of MLP classification, confirming our previous hypothesis that having overlapped root samples would increase the accuracy. Since the mined dataset is not specific to any target user's behavior, it is anticipated to result in less accuracy than the TM1 evaluation accuracy. In TM3 evaluations, due to the sample size differences across the labels in city-level dataset, we follow the same procedure in TM1 evaluations. The table shows the results of the evaluation where we employ tenfold cross-validation. The success of the city-level estimations when compared to the borough-level estimation is based on the elevation range and sequence differences across cities, which is reasonable. For TM3 simulated evaluations, we reviewed the simulation dataset with 35% overlap ratio for each city and performed the same evaluation. When the tables are compared, we noticed that the accuracy, recall, precision and F1 scores have increased for all classification techniques as expected. The improvements prove our previous hypothesis. Having similar patterns in dataset affects success of the attack. Let's move on to the image-like evaluations. The original datasets are unbalanced. There are various methods to deal with unbalanced datasets. Among these methods, downsampling and oversampling are the easiest ones to explore. However, downsampling leads to losing great amount of data, and oversampling raises the chances of getting lower accuracy because of the misclassified duplicated samples. Therefore, to deal with the unbalanced dataset, we utilize weight loss function and fine-tuning. In weighted loss function, by assigning a class weight that is inversely proportional to the sample size of the class, we signify samples of small classes while calculating the loss, thus their effect does not easily wear off. We also utilized fine-tuning. Fine-tuning is a common technique in deep learning. It is used for retraining a complex pre-trained model with another dataset. To address the unbalanced dataset problem, we take advantage of fine-tuning in a different manner. Namely, we introduced rounds and created a set of small datasets from unbalanced dataset for each round. As illustrated in this figure, several small and balanced datasets are created by randomly selecting samples. For each consecutive round, samples of one or more classes are discarded, and the round dataset is created from the remaining classes. The model is then trained with the round dataset that contains the least number of classes. At each step, the model is retrained using the same or different hyperparameters until all rounds expire. The dataset ordering of the rounds are reversed, since the impact of the smallest dataset would wear off if the model is trained with the same order of round dataset creation, which conflicts the whole idea. As illustrated in this figure, while retraining, the parameters of the previous model are passed to the model of the next round. But the hyperparameters of each round can be tuned accordingly. For instance, in the last round, where we include all classes, the learning rate can be reduced to find the loss minima. To observe the impact of the weighted loss function, we conducted evaluations also with unweighted loss function. We note that the unweighted loss function evaluation results are biased due to the unbalanced dataset. The table shows the maximum achieved accuracy for each dataset and method. Even though the unweighted loss function evaluation results are biased, the biased results remain behind 4 out of 8 evaluations. When the biased results are excluded from TM2 evaluations, the weighted loss function performed better than text-like and fine-tuning methods. However, in TM1 and TM3, the accuracy scores between methods are considerably close. Thus, we conclude that the weighted loss function improved the prediction performance primarily for TM2. Table also shows that fine-tuning methods outperformed other methods only for TM2, Washington, D.C. The difference between the fine-tuning evaluation of Washington, D.C. and others is that we were able to create only one round from the D.C. data. Overall, according to the results showing in these tables, the fine-tuning evaluation is not as successful as the weighted loss function evaluation. The main reason for this is the fact that we are losing certain portion of the data while creating rounds. Now I will briefly discuss what has been done in the literature. Although there is no directly related study to our work, location privacy is a topic that is related to various pieces in the literature. One study suggested that most location privacy breaches are caused since users do not know why or how to preserve location privacy. To this end, they developed a tool to examine possible privacy exposures of users in their social networks where the data is mostly collected from wearable devices. Another study aimed to increase the awareness of location privacy on geosocial networks by surveying 186 users, where 77% of them indicated they use location-based services often, several times a day. 47% of them reported that they were not aware that the location-based apps collect and store location information even though users select the private location option. Moreover, 43% of respondents were not aware that application may share the location information with third parties. Several attacks are devised to uncover supposedly protected locations. Experiments for revealing exact locations from trajectories with private zones are conducted on Strava. Researchers found the exact endpoints even when such users selected the private zone option. In another study, location trajectories of users are recovered from publicly available aggregated mobility data obtained from GSM operators. Another study showed that sharing data which reveals spatiotemporal features of users' mobility patterns on online social networks reveals sensitive information such as home location. In another study, it is shown that location-based social networks are vulnerable to identity privacy breaches by revealing the identity of the users by observing their mobility patterns. Now let me briefly summarize the main points. In this paper, we presented new attacks on location privacy using on-elevation profiles. The attacks are categorized into three types: predicting location by knowing the activity history of the target, predicting the borough by knowing the city of the target, and predicting the city of the target without any prior knowledge. The key contributions of our work are as follows. The first one is providing the concept that hiding the route of a workout and sharing only the elevation profile is not sufficient to preserve location privacy. The second one is defining a new attack surface by creating scenarios for possible threat models. And the third one is providing a machine learning approach to realize a new attack surface. To validate our attacks, we created 3 datasets by collecting data from athletes and mining data from a popular fitness tracking website and Google Elevation API. We pre-processed the datasets by employing natural language processing and computer vision approaches, and then employed classification techniques to predict the location from elevation profiles. We defined 3 threat models and evaluated each of them individually on the different datasets. As a result of the evaluations, we were able to identify the corresponding location of an elevation profile with accuracy between 59% and 95%. In the future, we will explore defenses such as devising and using route statistics that serve the same purpose as sharing elevation profile, which is demonstrating the roughness of the route while preserving users' privacy. For those of you who are interested, here are the list of references. Thank you for your kind attention. If you have any questions, please feel free to email me.